Now we will solve one more problem on compressor, reciprocating compressor. Uh, Going through the problem, it's a single cylinder. It's a single cylinder, double acting compressor. So double acting compressor in the sense, so compression is taking place in both the sides. So compression is taking place in both the sides of the piston. It's a reciprocating compressor and receives air at 1 bar and 17 degrees centigrade. So if we take the PV diagram, so it is taking air at 1 bar and the temperature is 17 degrees C. After that it is compressed to 6 bar. So this is P1 1 bar, P2 6 bar, P1 1 bar, P2 6 bar. So this compression takes place with the law PV power 1.25 is equal to, see, it's a polytropic process, and the cylinder diameter is given. So this is dia of the cylinder is given 300 mm. So here one more thing they have given, piston speed. Piston speed is 150 meter per minute. So piston speed is 150 meter per minute. So I will write speed is equal to 150 meter per minute. N is equal to RPM. N is equal to 100 RPM. N is equal to 100 RPM. Then calculate the power required in kilowatt for driving this compressor. So neglect the clearance. This is important, that we will discuss in the coming videos. So we are neglecting the clearance, and this is the data given. So what they are asking is power required in kilowatts. So we have to find power IP. So we have an equation for work input. Work input equation we remember, Win is equal to N by N minus 1 P1 V1 P2 by P1 N minus 1 by N minus 1. So this is how we can obtain work input. This is kilojoule per cycle. The equation is kilojoule per cycle. So we have to find out in terms of kilowatt. So to multiply, to get in terms of kilowatt, we have to multiply this W with the RPM. We have to multiply this with the RPM. This is one cycle into how many cycles are there, that much power we will get. But along with this power, there is one more side, that is behind of the compressor, is also working. So only the front face of the compressor or piston is used to compress the air, but in this double acting, both the sides of the piston is used to compress the air. That's why in this equation we will multiply with the 2. We will multiply with the 2, and N is in RPM. Let me substitute in terms of RPS. Let me substitute in terms of RPM. So W N then 2 for double acting, then divide by 60 to make this into rotation per second, RPS. But uh, we need to find out W in. N is given, 2 is there. To get Wn, what are the data we need? P1, V1, P2, P1. So P2 is there, P1 is there. P2 by P1 is 6 by 1. Then only unknown thing is V1 in this equation. So to get equation V1, we need to make use of this data. Meter cube per minute of volume of flow is taking place. So in the previous video I have given equation for speed of piston. Vs is equal to 2 times Ln. So this is one equation. Vs is equal to 2 times Ln, and hence N is given, Vs is 150, so L is equal to 150 by 150 divided by 2 times the RPM. So RPM is 100 RPM. So this is also in meter per minute, so this is also in RPM. So the unit matches. So what we get is, here L is equal to 0.75 meters. So L is equal to 0.75 meters. So with L 0.75, we have the diameter of the piston cylinder. So with the help of Vs to find volume, so we know that swept volume of the cylinder is area into the length. So this is the area of the cylinder, this is the length of the cylinder. So this gives the volume of the cylinder. So that is equal to, volume of the cylinder can be calculated. So area is pi into diameter is 300 into 10 power minus 3, 10 power minus 3 divided by d square by 4 into 0.75. So this volume of the cylinder we will get as 0.053 meter cube. So this is the V1 swept volume, that is volume of the cylinder. So this much of the volume of the air is taken inside the cylinder. Now all these values will be substituted in the work done equation. W in is equal to, N is 1.25 divided by N minus 1 is 0.25 into P1. P1 is 1 bar, 1 into 10 power 5 into V1 is 0.053 into P2 by P1 is 6 power, that is 6 by 1, again this is 0.053 2. So the P2 by P1 value is 6 by 1, 6 by 1, P2 by P1. So we will write 6 to the power n minus 1 by 1.25 minus 1. So this work done we will get as, so this W in is equal to, this is how much it is, 11.42 into 10 power 3 joule per cycle. This is W in. So we have W in, we know N, and we can find out IP. And IP is equal to 38.1 kilowatt. So using this equation, so this is the solution. Now we will discuss how to minimize the compressor work. So minimizing the compression work. So this we know one concept of compression. So this is the reciprocating compressor. So when the air is compressed, the temperature inside this cylinder increases. When the temperature inside this cylinder increases, uh, we can see there is a change in density. So if the density is less, then the work required to compress the air is also more. So here we have a technique where we can reduce the compressor work required. So we can reduce the compressor work required by using a cooling system. So with the help of cooling system, the specific volume of the gases can be reduced. So if we achieve lower temperature, then specific volume of the gas is also going to come down. Uh, thereby we can see the less work input required for compression. So we have the PV diagram which we have discussed earlier. So this is a suction. There are three different methods of compression we can refer. One is isentropic, then we have another compression, polytropic, and another what we have is isothermal, and another one is isothermal. So these are the three different ways of compression, where here this is adiabatic or isentropic, and this is polytropic, and this one is isothermal. So first one is adiabatic, polytropic, and third one is, this is isothermal, because here the area what I'm going to fill is less than the area of other two, that is adiabatic and polytropic. So TS diagram will look like this. So here this is isothermal process, T is equal to constant. This is 1 to 2, I will write dash to double dash to triple dash. So from 1 to 2 this is isothermal process, and 1 to 2 double dash this is polytropic, and 1 to 2 it's a adiabatic or isentropic process where entropy remaining constant, S is equal to constant. These are three different compression system what we can observe in compressors, but all these three has a different work equations. So W polytropic is equal to n by n minus 1 P1 V1 into P2 by P1 power n minus 1 by n minus 1. So this is the equation for polytropic work. In case of isentropic, W we have to substitute gamma. Same equation, P2 by P1 gamma minus 1 by gamma. So then next we have W isothermal. So here from 1 to 2 it can be written as, so if I take this as V1, this is V1 and this is V2, I can write integration of V1 to V2 P dV isothermal process is equal to P1 V1 power ln V1 by V2, which is equal to P1 V1 ln P2 by P1. So this is important equation that you have to remember. This is an important equation that you need to remember. So isothermal work done, this is an isothermal work done here, because this we get, because we know that PV is equal to C, that means P1 V1 is equal to P2 V2, therefore V2 by V1 is changed to P1 by P2. So using this we have replaced V1 by V2 into P2 by P1. Now with the help of isentropic process, then we have polytropic process, and with the help of isothermal, process we can derive some definitions or particular efficiencies that are called isothermal efficiency. These are some compressor efficiencies. These are compressor efficiencies. that is first one, efficiency. This is isentropic, or it is also called adiabatic, isentropic or adiabatic, which is equal to isentropic work divided by actual work input. Isentropic work input, isentropic work input by actual work input. So this is isentropic efficiency. This is important, so I request you to remember. Second one is compressor efficiency. So compressor efficiency is isothermal work divided by indicated work input. So here you can easily remember this, because isothermal work is the minimum work, but indicated work is work what is actually seen inside the cylinder. So indicated work will be always more. We cannot achieve isothermal work, 100% isothermal work. That is what compressor efficiency is defined as. Then we have third one. Third one is isothermal efficiency. Which is isothermal work divided by actual work. Actual work input. So what we see here is isothermal will be always in the numerator, because it is the minimum thing, minimum work. So if this is the minimum work, then for compressor efficiency divided by indicated work, for isothermal efficiency divided by actual work input. So isothermal efficiency can be improved by improving so how to improve the isothermal efficiency? So first we have an option to spray the water. This is water spray. Using water spray technique we can improve the isothermal efficiency. Then water jacketing, then using fins, then we have fourth one, intercooler. So this intercooler we will study in the coming video lectures in detail, but as of now these are the four general techniques that are used to improve the isothermal efficiency. So water spray is, the cylinder is sprayed with the water so that any temperature rise will be coming out of the cylinder, thereby temperature reduces inside the cylinder. That's why the isothermal efficiency will be more. Then we have water jacketing. So we will have a cylinder with the internal channel. So there will be a port. Through the port water will be made to flow from one around the circular section. So if you take this cross section like this, so water will be made to flow around this cylinder. So compression takes place at the center, so it absorbs all the heat. And other technique is fins. So this is very common techniques, so most of you have seen this. Using fins we can release the heat to the surrounding air. That's why we can see the cooling happens, and if heat is removed then isothermal efficiency will be more. Otherwise we can use intercooler. So if you have two stages, two or multiple stages, then from one cylinder to another cylinder, if you are passing the compressed air from one cylinder to other cylinder, in between these two cylinder we can have an intercooler. Again, this intercooler uses all these three methods or any one of these method to remove the heat. So this is how isothermal efficiency of the compressor can be improved. Now we will see how to solve a problem for three different compressor processes: isothermal, polytropic and isentropic processes. So what we see here is a single acting single stage compressor. It's an air compressor, single acting single stage reciprocating air compressor. The compressor has diameter 200 mm. So diameter of the compressor is 200 mm, and the stroke length, this is piston, so the stroke length is given, that is 350 mm. So these two will help us to find volume. These two will help us to find the volume. Then N is given. So this, the revolution of the compressor shaft is N is equal to 200 rpm. Then we have pressure 1 bar and 6 bar. So the compression is taking place from 1 bar to 6 bar. So compression is taking place from 1 bar to 6 bar. And that means P2 by P1 is 6. Then, so for this condition, we have to find out isothermal work, polytropic work and isentropic work. We will write down the equations for all these processes. The first process, isothermal process. First one is isothermal process. Isothermal work is given by P1 V1 ln P2 by P1. Then second equation we have polytropic. So that is W is equal to N by N minus 1 P1 V1 P2 by P1 to the power n minus 1 by n minus 1. Then third we have isentropic. This is same. Instead of n we substitute gamma. So the equation remains same. So here if we see, the unit will be in terms of joules per cycle. So it is not in terms of watts. This is not per second. But if any of this term here, this volume, whatever we are considering here, is in terms of meter cube, but if we take that as volume flow rate in terms of meter cube per second, so then we can get the unit as watts. So for that, to substitute here, we know this, and only unknown is volume. So we have the data required to calculate volume. Diameter is there, stroke length is there. So V is equal to pi d square by 4 into L, that is stroke length. So if we substitute that, pi by 4 into 0.25 into 0.35, that is we get 0.0171 meter cube. This is not flow rate. So this is cylinder volume. This is the volume of cylinder. But if we have to use V dot, volume flow rate, then it should be multiplied by the number of revolutions per second, that is suctions, how many suctions that it is going to happen per second. So it is 0.0171 into how many RPM is given. So they have mentioned 200 RPM. So I need to have in terms of per second, meter cube per second. So I will write this 200 suctions per minute. So I will make it per second. So this is V dot. So whatever we get is a V dot. It will be in terms of meter cube per second. So it will be in terms of meter cube per second. So next we have to substitute those values in this equation and get this work done in all three processes. So we will write down the data in the next page. So we have volume flow rate, V dot, volume flow rate V dot is equal to 0.0572 meter cube per second. So now first we will calculate the isothermal compression work. W dot iso is equal to P1 V1 ln P2 by P1. This is the isothermal compression work. Substituting 100 into 0.0572 into ln 6 by 1. This is P2. 1 bar is P1. That 1 bar is written as 100 into 10 power 3. 100 into 10 power 3. So here because 1 bar is equal to 10 power 5 pascals, and we will write 10 power 2 here, 10 power 3 here. Then so the calculation, after calculation we will get 10.26 kilojoule per second. This is not per cycle, this is per second. That is 10.26 kilowatt. This is isothermal work. So what we have now here is isothermal work. Next, moving on to the second type of compression, that is polytropic compression. W dot polytropic is equal to n by n minus 1 P1 V1 P2 by P1 power. This is n minus 1 by n. Substituting the values, will get so this is again pressure, this is V1 volume flow rate, this is pressure P2 by P1, and n is given, so we will get the answer same like this. W polytropic is equal to 12.7 kilowatt. So you can see here 12.7 kilowatt. So this is 10 kilowatt and this is 12 kilowatt. That means this, as we told, isothermal process work done by the curve So work done by the curve or area under this curve, which is isothermal curve, is less, hence we are getting the less work input. And so next, the third one, this is isentropic compression. W isentropic is equal to, similar to this equation, easy to substitute, gamma by gamma minus 1 P1 V1 V dot 1 so I will substitute the values. 1.4 same values, remaining values are same. Gamma is 1.4 minus 1 by 1.4 minus 1. So solving this, you should be able to get 13.38 kilowatt. This is sorry, this is also called adiabatic or isentropic. And if I draw TS diagram, this is PV diagram for three different process. For the same process, TS diagram I can write it as, because isentropic process entropy remains the same, sorry, so this is isentropic process, entropy remains same, so I am writing constant entropy throughout the process. Then this is isothermal process, so we have constant temperature, and this is polytropic compression, the curve comes somewhere like this. So with this answer, what we can find out is now efficiencies. We have to find out efficiencies. The first one is isothermal efficiency. Second one is polytropic efficiency. And the third one is isothermal, polytropic and isentropic. And isentropic efficiency. So it is nothing but isothermal work divided by actual work. It is substituted, isothermal work is 10.26 kilowatt divided by actual work. So in this problem they have asked to find out isothermal efficiency for all three types of compression: isothermal compression, polytropic and isentropic. So as they have asked for isothermal efficiency in the problem, here if we are missing this term, we can note it down as we have to find isothermal efficiency. So isothermal efficiency for three cases. So for all these three cases we have to find the isothermal efficiency, and that's why what we can see here is actual work will be the isothermal work. That means isothermal efficiency for isothermal process is 100%. For isothermal process, isothermal efficiency is 100%. For polytropic process, isothermal efficiency is, for polytropic process, isothermal efficiency is, isothermal work by polytropic work. So that is 10.26 divided by 12.7, that is 80.8%. So this is 80.8%. So for this polytropic process, isothermal efficiency is 80%. That means there is a 20% loss nearly, because the process is polytropic. Next, similarly, isothermal work by divided by, so isentropic efficiency is 13 point, 10.26 divided by 13.7, sorry 38, which is 76.6%. That means for isothermal efficiency for this isentropic curve or adiabatic curve is 76%. That means we can see the loss roughly around 25% nearly, because of the process what we have. So this is how you can analyze the efficiencies. And so this is about how to find the efficiencies of compressor for different types of compression process, that is isothermal process, adiabatic process and isentropic process.